Okay, for what we have crossing over into what will be referred to as substitution methods and exact equations. And so far, the first order differential equations we have dealt with have been separable or linear, or maybe both for that matter. But we're going to cross over into the realm where we might encounter some first order differential equations that are neither separable nor linear. And we can have, say we have dy over dx is equal to a function of x and y, where we have y as the dependent variable and x is the independent variable, and where substitution methods might come into play. And we might be looking at setting things up in terms of a different combination, where we can say we have a new independent variable v is equal to alpha of x and y. And now for what we have, just as a bit of an introduction, okay, to the substitution method with the variable b, I'm going to just take like an equation that is separable to begin with. Okay, now we have dy over dx is equal to x plus y, and along the lines of first order linear differential equations, I could isolate the x and move the y over and have like p of x is equal to -1, and then take the integrating factor. But I'm going to tackle this problem in the case of what we have with the v substitution. So what I have the derivative set equal, I'm going to have v also set equal. Okay, so we have a combination x plus y, and I'm going to set v equal to this. And I'm going to take the derivative with respect to x of v is equal to x plus y. So we have the derivative nx of v becomes dv over dx, and the derivative nx of the sum of x and y, we have d over dx of x becomes 1, and the derivative with respect to x of y, we have dy over dx. Notice we have for the introduction of the differential equation, we have dy over dx is equal to x plus y, and notice we have dy over dx, and if I put this in terms of what I have for the variable v, we have dy over dx is equal to dv over dx minus 1. And here we are looking at the same dy over dx, and now, so you have again dy over dx is equal to x plus y, and again just going back to what we had set up for v, we had that v is equal to x plus y. So I'm going to put anything that I have in x and y in the original statement at bay and just put in the variable v. And again we have dy over dx is equal to dv over dx minus 1, and so I'm going to set these expressions equal to each other and utilizing the variable v. So here we have dv over dx minus 1 is equal to v, and here in terms of the variable v, I'm going to be able to separate. But for what we have in the meantime, okay, I'm going to isolate the derivative dv over dx, and again have is equal to v plus 1, and here we can separate. So here we have dv over v plus 1 is equal to dx, and just taking the integral of the reciprocal of v plus 1, I'm just going to go ahead and say natural logarithm of the quantity, not the absolute value, but the quantity of v plus 1 is equal to x plus c. And then looking at taking the natural logarithmic base e as the base to which both sides are going to be the powers to which e is raised. So e to the natural logarithm of the quantity of v plus 1, that is a v plus 1. For e to the x plus c, this translates to e to the x times e to the c. And again, e to the c is just a constant. Okay, so we have e to the c goes to a, thus we have a times e to the x. And so we have v plus 1 is equal to ae to the x, and isolating v, we have v is equal to ae to the x minus 1. And again, going back to what we had v to define, we have that equal to x plus y. Okay, and so putting v in terms of what it had been substituting for, we have x plus y is equal to a times e to the x minus 1. And getting y by itself, we have y is equal to a times e to the x, and then we have minus x minus 1. Now, let's say if we have an equation that is neither linear nor separable. And we'll say that we have dy over dx is equal to the square of x plus y plus 4, quantity squared. Okay. Alright, so I have dy over dx is equal to the square of the sum of x and y and 4. And I'm going to use v substitution, okay, and to be able to keep it linear as much as possible, I'm going to have that v is equal to the expression that is being squared with dy over dx. Okay, so we have the square of x plus y plus 4, but for v, I'm going to have that it is equal to x plus y plus 4, and taking the derivative with respect to x, and I'll just do it in one sweep. So we have d over dx of v is equal to d over dx of x plus d over dx of y plus d over dx of 4. Okay. So the left hand side, okay, we're going to have dv over dx. Again, the derivative with respect to x of x, that will go to 1. And d over dx of y, okay, so you're going to have dy over dx. And for the derivative with respect to x of a constant, okay, well that's just going to become 0. Okay, and so isolating dy over dx, we're going to have this bit of history to repeat, whereupon we have dy over dx is equal to dv over dx minus 1. And if you notice, okay, having set v equal to x plus y plus 4, reverting back to the original equation. Okay, so dy over dx we have as the square of x plus y plus 4, and with v set equal to that sum, well, in terms of the variable v, we have that dy over dx is equal to v squared. And looking at what we have now, okay, so you have both forms of dy over dx are in the form of the variable v. So doing a bit of interlocking, and now taking what we have in dy over dx and putting in terms of the variable v. So I'm just going to switch the order. So now we have dv over dx minus 1 is equal to v squared. And what I can do is isolate the derivative. So you can just add 1 to both sides. So you have dv over dx, okay, is equal to, you can say either v squared plus 1 or 1 plus v squared. And so in isolating dv over dx, you can say v squared plus 1 or 1 plus v squared. And the reason I have 1 plus v squared is that I have a sum of squares, and I'm going to divide the equation by that and simultaneously multiply by dx. So you have dv over 1 plus v squared is equal to dx, and integrating over both sides. And now we're going to have, for the reciprocal of the sum of squares of 1 and v, okay, that's going to be an inverse tangent or arctangent. In this case, we have the arctangent of v is equal to x plus c, and putting in terms of v, so I'm going to be taking the tangent of both sides. So the tangent of the arctangent of v, okay, that will go to v, and that is equal to the tangent of x plus c. Now remember, going back to what we have with x and y, so we had v was equal to x plus y plus 4. And so we're going to have, upon isolating y, so y is going to be equal to the tangent of the quantity of x plus c, and then we have followed by the subtraction of x as well as 4, and that will be the outcome of what we have for y in this particular inseparable differential equation. Okay, now let's say we have solving for the differential equation whereupon we have the derivative dy over dx is equal to the quantity of 4x plus y squared. Okay. And what I can do here, okay, if I write in the substitution variable and create a linear statement, linear in terms of v as well as x and y, I can just say that v is equal to 4x plus y. And just setting the stage of putting this equation in terms of dy over dx. So again, if I take the derivative with respect to x, okay, so you have d over dx of v, and you can say either d over dx of 4x or 4 times the derivative in x of 4x. Regardless, okay, this will lead up to the same term. So this time around, okay, we have dv over dx is going to be equal to 4 plus dy over dx, and putting the derivative dy over dx in terms of the variable v. So we have dy over dx is equal to dv over dx minus 4. And again, so you had v was equal to 4x plus y. And with the first display of dy over dx, you have the square of 4x plus y. And in terms of the variable v, okay, we'll say that dy over dx is equal to v squared. Okay, so just kind of transporting what we have here. And since we're working with the same dy over dx, and now just taking what we have in terms of the variable v, so we have dv over dx minus 4 is equal to v squared, and isolating the derivative. Okay, so you have dv over dx is equal to 4 plus v squared. And in terms of the variable v, I can separate. And we have upon integrating. Okay, so for dv over 4 plus v squared, okay, we're going to end up with the arctangent of what is going to be v over 2, and not just the arctangent of v over 2, because I'm looking at, again, I have the a value is going to be at 2, so I'm looking at 1/2 the arctangent of v over 2. So just a bit of a reminder. Okay, so if I have du over a squared plus u squared, and where I do not have any special u substitution required, so this would be whenever a times the arctangent of u over a followed by the constant. Alright, and for what I have to the right, because we have is equal to x plus c. So we have the arctangent of v over 2 is going to be equal to 2x, and I'm going to say 2c, but I'm just going to use a different variable. So we have with alpha, letting alpha represent 2 times c. Okay. And now, so undoing the presence of arctangent, okay, I'll just go ahead and take the tangent of both sides, just like what I did earlier. So you have v over 2 is going to be equal to the tangent of 2x plus alpha, that v is equal to 2 times the tangent of 2x plus alpha. And again, from earlier, I had set v equal to 4x plus y. So just back substituting. So we have 4x plus y is equal to 2 times the tangent of 2x plus alpha, and getting y by itself. So we're going to have, for the general solution, we'll have 2 times the tangent of 2x plus alpha minus 4x.